So far in our discussion of groups, we've been using this kind of awkward notation G under triangle for a group with a binary operation named triangle. And it's been kind of awkward to be using, but I've done that intentionally to make you understand that the binary operation does not have to be one of the usual arithmetic operations that you're familiar with from lower level math courses. But it's very awkward notation, and in this video, I want to introduce some notational conventions that are used inside modern algebra. And the first convention is that in an abstract group and in most groups, we use what is called multiplicative notation. And multiplicative notation basically says that instead of writing this triangle, we'll write star for the group operation. And in an expression like A star B, we will shorten that to just AB. The group identity element is usually written in one of two ways. It is usually written as either an E, or in some circumstances, it is written as a 1 sub G, or even just a 1. And let me make these actually look like number ones. The right inverse, which remember is actually a two-sided inverse of an element A, is usually written as A to the negative 1. We do not use fraction notation, and I want to make that as a warning. We do not use 1 over A for the inverse elements. And there's a reason why, and I kind of want to illustrate that. So let's think about why. So why don't we use 1 over A? Well, the easiest way of thinking about this is to think about a group like GL2 under its times. If I take a matrix like 1, 2, 3, 4, that does belong to GL2, and its inverse matrix, if you go through the inverse matrix formula, can be shown to be minus 2, 1, 3 halves, minus 1 half. And this notation makes perfectly good sense. But what would 1 over a matrix mean? That's meaningless garbage notation, and this is why we do not use fraction notation for multiplicative inverses. Continuing the multiplicative notation theme, let's look at some other expressions in the group G under star. So that is our group. If I have an expression like A star A, and I keep going star A, and this is made up of n copies of A, it's no surprise that we're going to shorten that and read that as A to the n. If we have A inverse times A inverse times all the way up to A inverse, and we have n copies of A inverse, that would normally be written as A inverse raised to the n. We are tempted to shorten that using exponent rules from arithmetic and write that as A to the minus n. This is actually going to be a theorem, because we can also think about the expression A times all the way up to times A inverse. And this, of course, is n copies of A. And this would be A to the n's inverse. And again, we would like to be able to shorten that and simply write that as a to the minus n, but this is also going to be a theorem, and the reason this is a theorem is that we have to show these two things are equal. So the theorem is going to be that those two expressions are equal. For the time being, I simply want you to be aware that yes, the notation that you're familiar with in terms of exponent rules is going to go through just fine. So those are our conventions for multiplicative notation. The problem is that some groups have addition as the binary operation, and I want to talk about that as our second convention on notation. So I'm simply going to make this as a note. Some groups have some kind of an addition for the binary operation. And we've seen many of these in the examples of groups that we've already seen before. And so what I'm going to basically be thinking of is if I have a group that has an additive binary operation, first of all, this is referred to as an additive group. And we get a different set of conventions for the notation. And so let's look at the notational conventions here. First of all, what we're going to do is we are not going to shorten the expression for the sum of two elements, so that does not get shortened in any way. The identity element in additive groups is usually written as a 0, or if it's important to denote what the group is, we say a 0 sub g. The inverse elements are usually written with a minus sign. So we use minus a for the inverse of element A. And this is just a convention for all notation. Now, if we have repeated binary operations, the notation looks slightly different. So let's look at that. If we have a plus a plus a plus, and we go all the way up to a, and there are n copies of a, we traditionally write this as NA. Now, it's important to understand that this NA is not a multiplication inside the world of real numbers. This means n copies of A added together. And if we have minus A plus minus A plus minus A plus all the way up to minus a, and there are n copies of minus a, well, that would be technically n times minus a, but we want to think in terms of ordinary symbol manipulation, and we would like to be able to write that as minus n times a, but this is going to be a theorem. Because we can also think in terms of the additive inverse of a plus all the way up to plus a, where we've got n copies of a, and that would technically be minus n times a, the additive inverse of n times a, but again, we would like to use the convention that that's just minus n times a, so that's going to be a theorem, and it's going to be based on the same kind of fact. We will have to show these are equal. So that will be the theorem, that these are equal. Now, since there are two kinds of notation used for groups, the final thing that we need to look at is how we literally translate from one notation to the other. And that translation skill is important, and I want to talk a little bit about that. So, most group theory theorems are written with multiplicative, let me correct my spelling mistake, multiplicative notation. We must translate to additive notation before applying a theorem to a group that is written additively. So let's go to the next page to make the translation idea much more easy to follow and explicit. So translation. And I'm going to take the time to put in some nice vertical lines because what I really want to do is keep this table nice and neat. And I've got multiplicative notation, but let's spell it right. And I've got additive notation. And in a typical multiplicative group, G under star, and a typical additive group would be G under plus. The identity would usually be written as an E over in a multiplicative group, but when we do the translation, that's going to become a 0 in an additive group. If we look at inverses, we're going to be looking at A inverse in a multiplicative group, and in an additive group, that's going to look like minus A. If we look at the expression AB, which could also be A star B in a multiplicative group, when we translate that, that's going to look like A plus B. If we have an expression that looks like A times B inverse, that's going to wind up needing to be translated to read A plus minus B, but it is traditional to shorten that to A minus B. If we have A to the n in a multiplicative group, that is going to look like n times, and let me get rid of that. That's going to look like n times A in an additive group. So this is multiplicative notation. This is additive notation, since the top of our table went away. Let's see. Let's continue that vertical line down. And because we have just a couple more of expressions to be thinking about. If we have A to the minus n, that's going to look like minus n times A. And finally, if we have A to the 0 over here, remember that's just another name for the identity element, but in terms of powers, what this is going to look like over here is 0 times A, and 0 times A is again just going to be the group additive identity. This 0 is actually the integer 0. This is the group element. And that list of things is pretty much all that you need for translating any multiplicative group theory theorem into additive notation.